Hello, everybody. This is the lecture on molecular modeling of polymers. And in this lecture, I will give you a short introduction to polymers, what they are, where they come from. Then we will talk a little bit about the chemical structure of polymers, in what kind of architectures they can come. Then we will talk a little bit about how to describe them in terms of theory. So this will be polymer model. There, the polymer statistics will play a big role, and then I will tell you at the end what are the standard models on how to simulate polymers, and then we're done. So let's first have a little look on history of polymers. So the name comes from the Greek polymer, meaning many particles. So the first one who suggested the existence of polymers was Hermann Staudinger, and he got for this discovery the Nobel Prize for Chemistry in 1953. So at that time, remember around the 1920s, it was not possible really to see polymers via some imaging strategy because the light microscope can only resolve sizes of up to a few hundred nanometers, so let's say 500 nanometers, and most of the polymers lie below that scale, so you just simply can't see them. Um, for the longer polymers, where you get coils of the order of 1 micrometer, you can see that, but people believed that polymers were just disordered conglomerates of small molecules, so they were not covalently bound. Now, how did the proof of the existence of polymers proceed? Well, that came about in 1928 when Peter Debye managed to look at X-ray scattering data and basically explain the features which he saw there by relating it to what is known as the random walk model, and then he could derive scattering functions, and then people were convinced really that polymers existed. Other important people in polymer theory are Mr. Kuhn here, Paul Flory, who got a Nobel Prize for Chemistry, Sam Edwards, who unfortunately is dead by now, who introduced Feynman path integrals for theoretically describing polymers, and Pierre-Gilles de Gennes, who also won a Nobel Prize for physics, basically for the physics of soft matter, for his work on liquid crystals and polymers. Now, up to modern times, within 10 years of polymer science, the attitude changed from, well, polymers don't exist, like people were very skeptical in the 1920s. Then it was like, well, maybe it's true when they were discovered, and up to the point where you say, oh, well, that's all well known. Already in 1928, DuPont brought about the first product based on polymers, which was nylon, made for nylon garments. And in the 1930s, already PVC came out as a Teflon, which basically changed our way of cooking, and polyurethane and polystyrene polymers appeared to become prominent in industry. What we say plastics, that means actually that we're able to model it, to mold it into form. And now, when time passed by, I mean, plastics are basically everywhere, or polymers are basically everywhere. Just think about high strength fibers in clothing and everywhere else. But nowadays, let's say the last 20 years, there has been a big uprise also on organic electronics, where we would no longer, where you think of flexible electronic structures, where solid state electronics, there might be some advantages with organic electronics. Solar cells and polymer batteries are basically the best known examples for that. Now let's turn to some examples for polymers. Basically, how people did that long time ago was that you started out with a base material for a polymer, which is here like ethylene, which has a double bond between the carbons. If you go to a gas phase reaction, this double bond can break up and react with other ethylanes in a polymerization reaction, and then you can create what's called polyethylene. Now, the structural unit is always the same, which is the CH2 unit. And the way we describe polymers is that we just write down the basic monomer and set down here the degree of polymerization so that we know how long the chain molecule actually is. Other well-known examples are polystyrene, which has a different macromolecular group here, or polyvinyl chloride, known as PVC, which has this kind of unit here. I mean, the physical chemistry of polymers can be quite involved, and I just want to sketch a few things here. Because if you have more than one group attached to a main carbon atom, there are, of course, different spatial arrangement possible. There are different tacticities involved. So if you have polymers which always arrange in a completely regular attachment, then you call that isotactic, which always the same arrangement in what is called the tetrahedral angle. If you have no regularity in the chemical structure, then they are called atactic. So that means it's completely random. And if you have an regular and alternating attachment, so that you have angles which are cis, trans, then you call it a syndiotactic. So tacticity is sometimes important if you would like to understand things on a very small level. We talk about a homopolymer if there's only one single type of repeat unit. These were the examples I've just shown you on the other side. If you have more than one type of repeat unit, then we'll talk normally about a copolymer, and it's usual to take these different blocks of a polymer, just call them A and B. And of course, now we have another type of randomness here, because these blocks can come either in a regular structure or they can come completely random. So if they are random, then we'll talk about a random copolymer. If they come in blocks, so you have always type of A monomers, and then you have type of B monomers, and then it can be followed again by some A monomer or by a C monomer, then we're talking about diblock, triblock, or multiblock copolymers. And then normally we say if it's an AB copolymer or if it's an ABC copolymer, and we discuss also how many blocks there are. So the names can be pretty complicated, but out of these complicated names, then you can already infer something about the structure of this polymer. Another point is what I showed you in the beginning is, of course, that you just had a linear polymer. That means the polymerization would just continue, that you would just get one single chain of a polymer, and this is called a linear polymer. But you can already imagine that if I have the linear polymer and if it back bites into its tail and it will form a ring, then we have a ring polymer. But for many monomers, there are much more complicated structures possible. So you can have polymers with short or long chain branches, which are called in general branched polymers. You can have polymers where they have grafted oligomeric side chains, sometimes also called bottle brush polymers, depending on how densely and how long these side chains are. Then you can have star polymers, and the number of arms would be then an N-arm star polymer. You can have networks of cross-linked chains, which is a gel-like phase, or rubbers, for instance, an example for a cross-linked network. You can have dendrimers, where you starting out from the central point, you have always this thing branches into two. So here it branches into two, and the next level it branches into two, and there it branches into two, and these different levels are then called generations of these dendrimers. And once you have many generations, you can imagine, I mean, this thing just branches like hell. Then we can have colms, we can have H branch, we can have ladder polymers. So imagine what could happen, and it definitely exists in nature. So the polymer architectures can be really very complicated, but mostly we are really interested in linear or maybe stars or maybe rings. Polymers can come up in different phases, let's say. The most known things are probably polymer solutions or polymer melts. I mean, you either dissolve a polymer in some organic solvent, and this is the solvent necessary to dissolve uncharged polymers, because the backbone is normally based on carbons, and carbon is a very hydrophobic moiety, and so you need an organic solvent in order to dissolve it. But if you have charged polymers, for instance, then you introduce hydrophilicity, because charge is like water, and then these polymers would be water soluble, which is the case for most biopolymers, or which is the reason for most biopolymers why they are charged, because then they are soluble in water, and this is of course what the body needs. If you don't have any solvent and you heat polymers up, then they melt, and we would call this a polymer melt. Of course, if the temperature is very low, polymers can also crystallize, and then we would talk about crystalline polymers. But polymers normally don't crystallize regularly because of their large conformational entropy they have, so they can never arrange in some really favorable way, and so they are normally glass formers. Now let's continue to talk about polymer solutions, and there are two concepts available basically. One distinguishes between a dilute solution of polymers. That means you have only a few polymers in the solution in such a way that, I mean, we'll talk about conformations later. Polymers form melts, they have some extension, and the extension is here depicted that they form here some sort of spherical coils. If these spherical coils of the single polymers are sufficient distant away, then it's called a dilute solution. Then there is a certain concentration which is called the overlap concentration. And if you're above the overlap concentration, then polymers pervade into each other and you are in the semi-dilute solution regime. The overlap volume fraction is defined as that volume fraction where the monomer volume times the number of monomers in a chain make up exactly the chain volume, and then that definition leads to the overlap concentration, where you simply map the volume fraction phi star into C star by multiplying by the polymer density. And pictorial, you can think about that if your number of polymers which are in the solution with a certain radius make up the whole volume of your solution, then you are at the overlap concentration. Okay, this is about the origin of the flexibility of polymers, and I will do this here for the example of polyethylene. So if polyethylene is a very simple polymer. So again, the bond length is fixed, whereas the bond angle actually has various possibility to adjust itself. The tetrahedral angle, which is the one between, it's a four-body potential between, let's say, these 4 points. So that's the angle of the two planes which are formed by these three and these three carbons can rotate, is also almost constant. So what can change is the bond angle potential phi, which, and here what you see is depicted the rotation potential of the rotation angle. So if that rotates around 360 degrees, that are the possible numbers, you see that the minimum lies actually in the so-called trans configuration, that it is in this case 0, but there's of course a relaxation angle phi here, and that for all the potential has two further local minima. They are not global but local, which is the gauche plus and the gauche minus. And so therefore the local minima just have just a difference of 0.8 kBt. So this is easily thermally accessible, although they have to cross a barrier. But nevertheless, the polymer can, due to thermal fluctuations, overcome these rotation barriers, and basically resides more often, of course, in the trans, less often in the gauche, and of course less often here where the maxima was. But all different isomeric rotational states can be occupied, and this leads to a large conformational space, and this basically gives the polymer the flexibility to explore many conformations, and this is why we can really describe a, a polymer despite the fact that these bonds have preferred angles and distances. We can describe it as a random walk with the Gaussian statistics. Let's go and talk about how can I construct an analytical model for a polymer. That is actually, I mean, this is what Debye has done in order to explain his X-ray structure pictures. And the idea was that let's assume we wouldn't know about this tetrahedral angle, but we would say that in principle, the polymer might have a fixed bond length, but it's completely free to rotate into any position. And then we are actually by a picture of a random walk. So that means if, and the random walk has a walk length basically of the bond length. And now when I start at point 0, I can go with 1 wherever I want to go within this spherical volume, and we have the same thing here. And I can construct actually all possible walks which are possible for a certain number of linkers, and that you can do by looking at the binomial distribution which you get from a random walk. And then we can actually write down the partition function for an ideal Gaussian polymer, as it is called. So if we're talking about a freely jointed chain, that it's equivalent to a Gaussian polymer. And we can talk about what is the distribution, for instance, of the end-to-end vector. And the end-to-end vector would be just the vector which connects the beginning of the polymer chain here to the end. The in-between vector are called the bond vectors. And in this way, we would like, or we can actually, we're mathematically able to talk about the average distance of a polymer. And because it's a random walk, the feature is that the average end-to-end vector length is actually 0, because a random walk, just think about a one-dimensional random walk, it's as likely to go to the right as it is likely to go to the left. So if you do it an infinite number of times, the average is just that you don't walk anywhere, and this is what this average tells us. But the second moment of this distribution, which is the end-to-end distance squared, that is non-zero, and that is equivalent actually to the idea of diffusion, where you also have the mean squared displacement. The average displacement of a diffusing particle is 0, but the mean squared displacement is non-zero. And therefore, diffusion is also modeled as a random walk, and therefore the diffusion problem and that of the conformation of a polymer have basically or share the same mathematics. Now, an important point or measure of this extension of a polymer can be the end-to-end vector squared, but it normally is easier to measure the radius of gyration, because that is what you get out of static light scattering, for example. And here is just written down the definition of the radius of gyration. This is basically just the classical definition, nothing weird here about it. You can set all masses to unity, then this is the center of mass vector, and it's basically the average of the distance of the bond vectors to the center of mass vectors squared. And out of these simple examples, following relations can be proven, so that the average end-to-end vector squared distance over the average radius of gyration squared distance for an ideal chain, so a Gaussian chain, is 6. The ratio for a rod would be 12. And if you would look at a distribution of a uniform sphere of radius r, where you have placed your end-to-end vector over the gyration radius, then you get 5/3 out. This is just a mathematical curiosity, but if you, for instance, compute these values in your simulation, then you have also an idea of what kind of statistics your polymer obeys. Now let's have a look at the end-to-end distance distribution. I was telling you it can be mathematically described by a random walk of n segments. Now, because I told you it's equal, I mean, if we do it discretely, we get a binomial distribution, but applying the central limit theorem, we can convert that actually to a Gaussian distribution. And using a Gaussian distribution is analytically, of course, very appealing, because then we can do many analytical calculations. And this is what basically is written down here. So P of R of n is the distribution of end-to-end vectors for a continuum random walk of step numbers big N. And this would be a Gaussian, and you see it's centered around 0. Normally, we are not interested in this distribution so much, but we are rather interested in the distribution of the length of the end-to-end vector, and that can be converted into the following formula. And then you see that if we rescale everything accordingly, then we get a nice form like this. We rescale here basically by the expected distance of a Gaussian random walk, because like in the diffusion problem, the mean squared distance is proportional to the time. If we map this onto a polymer, this means that the average end-to-end distance squared is proportional to the numbers of monomers. And that should ring a bell, because how can that be? This means, of course, that the size of a polymer behaves like a fractal, because if you would just take 10 pencils and you stack them on to each other, then of course the squared distance would be proportional to the square of the number of pencils you use. But because you have a polymer which has conformational possibilities to explore all points in space, then this goes just like linear in n, or r goes like the square root of n. So this is why one uses here this normalization. Now be just aware of a little thing, because we used the Gaussian approximation. That of course means that there are also possibilities for there will be probabilities to see end-to-end vectors which are larger than R max. And R max is the distance where we assume that there is that the bonds basically cannot break, and they have a fixed length. So this is sort of unphysical, but under normal conditions doesn't disturb our analytic calculations. Now here is an example which I make a little bit louder, so maybe you can hear that. People have looked at how does the size of a polymer, namely here the hook of a rubber band, changes with temperature. And what happens here is that the tip of the hook raises up by a total of 10 millimeter if they just use the hair dryer and heat it up by, I don't know how much you can heat it up, probably 40 degrees or so. I mean, a hair dryer gets pretty hot, and so that tells us something funny. So you heat up a polymer and it becomes shorter. Now, why does this happen? Because if you heat up a piece of metal, it definitely gets longer. We know that if we want to make things larger, we heat them up. But this is because the elasticity of normal material is basically ruled through their elastic behavior with their energetic bonds. Now, a polymer basically doesn't have energetic bonds, because we said the points are non-interacting. There's a constant bond length. And the only thing a polymer really has is entropy. And remember, for the free energy, we have basically, it's the internal energy, which is 0 for a polymer, minus kBt times the entropy of a polymer. And the polymer now has a lot of entropy. And if you go through these calculations, which for instance you can find in the very good textbook by Rubinstein and Colby, then you can calculate what is the free energy of a polymer, and it's basically 3/2 kVt r squared divided by n over b squared. So r squared is the extension of the polymer, which we know goes like nb squared. So this is basically a unitless quantity, and this law basically, if we say we have a prefactor proportional to r squared, it looks like Hooke's law. And Hooke's law has a spring constant, and the spring constant is kVt divided by n over b squared. So the spring constant is actually telling us that if I increase the temperature, the spring constant becomes stronger. So the polymer gets stiffer, which is, as I said, exactly opposite to the energetic elasticity, because everything, when you heat it up, it becomes softer. Now here it becomes stronger, and this means if you go through the calculation also, that you can show that if you raise now the temperature, then the polymer reacts because it can assume more conformation, the conformational space gets enlarged, then actually the polymer starts to shrink. And we saw this on this YouTube movie. Yes, that is true. Now there are things you can derive from polymer theory. I won't go really into that, but for polymers, different scaling regimes exist, and these scaling regimes only hold, of course, in the limit of large n. So whenever you do computer simulations with finite n, because we can't really go too far, then you will see glimpses of that you asymptotically approach these values, but you probably will not always find exactly these values. So one says the polymer scales like n to the power of nu, and this nu is called the Flory exponent, because Paul Flory was the first one who looked at that extensively. So we have actually different exponents depending on what kind of environment the polymer lives. So in our mathematically easy random walk or Gaussian, or sometimes also called ideal chain limit, or people also talk about a theta solvent, the polymer extension scales like n to the power 1/2. So we take the square root of n for r. That means the Flory exponent is 1/2. The name theta solvent I will explain in a second. Coming to the next point, which is the self-avoiding walk. This is also called a real chain or a polymer in a good solvent. Then we find an exponent of 0.63. This 0.63 point means this is a regular, a real number, which there is no good theory to compute that. You can do that via looking at the statistics of a self-avoiding walk. I mean, this is basically what people have done, and so this number is known for a few digits, but you don't need to care. There's actually a very nice but hand-waving derivation by a Flory, which comes up with the number 3/5, which has been used a lot in polymer theory, because it's close enough to 0.6 of this self-avoiding walk value, but which allows an easy calculation, and also the derivation of scaling laws with some meaningful rational numbers. Now we have a third case where we say the polymer is in a poor solvent, and there the Flory exponent is 1/3 or 1/3. So that means that the extension grows with a power of 1/3, which means the extension grows like a sphere. And that can also be explained because a polymer in poor solvent means that if the solvent is poor for the polymer, meaning that the polymer doesn't get really nicely dissolved in the solvent, so it tries to actually just have contacts with itself, because it's a finite object. Of course, it doesn't work so well, so it can just coil up in a least possible, or in the conformation where it has the least contact with the solvent, and this would be a spherical globule, and therefore this is why the Flory exponent is 1/3. Now you can rationalize further. If you are in a good solvent, the polymer is of course happily dissolved, But why is it then not the ideal case? Well, because a real chain has always some interactions, so it rather behaves like a self-avoiding war than like a Gaussian chain. But if the solvent now is poor, that means there are some attractions. When these attractions are just as big as to cancel the excluded volume interactions, then you are in the case of a theta solvent. So you have a solvent which puts some attractions in there, and they just cancel basically the the real chain excluded volume interactions, and this is how we end up with 1/2 in a theta solvent. And then, of course, the last case is if you have charges on a polymer. These are so-called polyelectrolytes, which you've heard about in Alexander Schlei's lecture. Then these charges repel each other on long scales, and this leads then to a scaling behavior of nu equals to 1, which is the normal macroscopic behavior of metals or wood or whatever. Now, here just a small glimpse of how the Flory scaling theory has been derived. Flory just said, okay, let's dissect the free energy of the polymer with another term. So here's the Flory free energy divided by kBt, so then it's dimensionless. And so you see here the free energy, as we had before, was this r squared over nb squared. So this is the free energy of an ideal chain. And then he added just a repulsive term, which is the second virial interaction of particles, and the second virial is proportional to n squared over r cubed, because it's just the way how the density gets introduced here. And we have the second virial coefficient. And Flory says, okay, if this is my total free energy, then the extension of my polymer will probably be such that this free energy is minimized. And this is always the Flory approach. You have to write down some reasonable free energy for your chain. Then you take the derivative, set it equal to 0, and see what comes out. And in this case, what comes out, because you can set this up for any dimension, how the interaction, the virial interaction looks like. And then you get a Flory exponent which looks like 3 over d plus 2. So d is now 3. We are at 3 over 5. And this is the Flory exponent 3 over 5 in 3 dimensions. If we just look at different dimensions, then we will see that this simple Flory approach is exact in 1 dimension. It's exact in 2 dimensions. It's not exact in 3 dimensions, but again, exact in any dimension higher than 4. And this comes about because 4 is the upper critical dimension in the theory of critical phenomena. Now, another approach to describe the statistics of polymers goes through Blobbology. I will leave it out here in this talk more or less, but I would like that you at least have heard about this. This is that what Degen has pioneered. It's sometimes also called the Degen scaling theory. So if you're interested, you can look at this book from Degen, The Scaling Concepts in Polymer Physics, where he lays the theory out. And the idea is that we should look at sufficiently small parts of the chain, because then we can think about them as being unperturbed. And these small parts are then called blobs. And here's a pictorial view of how a polymer might look like. So you have here the polymer coil. It is a random spaghetti, let's say. But this spaghetti can be chopped up in these blobs. And if you then make reasonable assumption about the statistics inside the blob, namely that it's an ideal chain inside, you can derive numbers for the monomers inside a blob and the blob size. And the knowledge about this yields then simple power law scaling relations. And that has been a real powerful pen and pencil approach to understand a lot of conformational properties of polymers in bulk and also in confined geometries and for brushes and whatever. Okay, now let's talk about the hydrodynamics of polymers. The hydrodynamic radius of a polymer is defined as the following. So the inverse radius, average inverse hydrodynamic radius, is given by looking at the average distances between all monomers, basically. And that is a quantity which can be measured actually in dynamic light scattering. Let's think a little bit about how the hydrodynamic radius is important for diffusion of a polymer, because we're now interested in the dynamics of a polymer. Now let's recall that there is an Einstein relation between the diffusion constant, d0, is basically inverse proportional to kBt over the friction coefficient. Now, if we think about spheres, we know that there's the Stokes relation, that the friction of a sphere is given by 6 pi eta, where eta is the viscosity of the medium times the radius of the sphere. And that leads to the Stokes-Einstein relation, that the diffusion of a sphere is given by kBt over 6 pi eta r. Now, what kind of relation does that have for polymers? Well, in polymer dynamics, there are basically two dynamical models around. First one is known under the name Rouse dynamics and doesn't include hydrodynamic interactions. And the idea in Rouse dynamics is very simple. Namely, you say, well, each of the monomers of my polymer contributes to the friction coefficient of the whole object, just its own friction coefficient. And so if I have n equal monomers with the same single monomer friction coefficient gamma 0, what I end up with is that the friction of my whole polymer should be given by n times the single monomer friction coefficient. Now, if I know the friction coefficient, I go to my Stokes-Einstein formula and I say, to my Einstein relation, basically, and I say, I just introduce my friction coefficient, and what I see then is the diffusion coefficient of a Rouse chain will behave like 1 over n. That means the more monomers I put on my polymer, the more or the slower it will diffuse. Now, as I said, this assumes that there are no hydrodynamic interactions between the single monomers, and therefore there's also no difference if you have an end monomer or a monomer inside the chain. And if you have now a polymer in a dilute polymer solution, sorry for that, then there's another theory which is called or runs under the name Sim dynamics. And there the idea is different. Basically, you say, well, I will have a n-dependent friction coefficient. Let's call it gamma z for Sim. And that the idea is I look at the polymer coil as if it would, or which behaves as a frictional object dissolved in the solution. And because the chain extension or the radius of my sphere depends on the solvent quality, I just apply now Stokes formula and say, okay, my friction coefficient then should be just 6 pi eta r, but r is a function of n. And I just told you the scaling relations in my previous slides, and this say I have to include here r to the power nu, where nu is the Flory exponent, and then just dependent on in what kind of solvent I am, I will get a different relation. And the relation is that my diffusion coefficient, according to Sim, should scale with the numbers of monomers, not like n to the power minus 1, but like n to the power minus nu. And I can tell you, if you just do a Langevin dynamics of a polymer, that's a point I will come later to, then what you will see is actually that your polymer will behave, the diffusion coefficient of the polymer will behave exactly like this formula here. Actually, you should get that exactly out if you do Langevin dynamics, namely the gamma of the Langevin should be exactly the one here seen in the prefactor. Now, if you switch on hydrodynamics, for instance, via lattice-Boltzmann simulation, then this should change, and you should actually see that the diffusion coefficient now scales with some Flory exponent. The Flory exponent is the one depending on what kind of interactions you add to your polymers. If you use an excluded volume interaction, then it should be roughly Flory, 5/3. And if you have electrophoresis, then of course things again change. Now, also ZIM is not, let's say, the best, even in hydrodynamics. The best fit you get actually if you apply Kirkwood-Zim theory, which says that the diffusion coefficient of a polymer is a combination of Rouse and Sim. You have one term which goes like 1/n, and then you have another one which scales like the hydrodynamic radius, and the hydrodynamic radius basically scales like n to the power minus nu, and therefore you have a combination of the two. Now let's have a little look on how to simulate polymers in your computer program. And as I said, the conformational properties of a Gaussian polymer are that of a random walk, and a random walk can be realized basically very easily by a bead spring model of a polymer. So you simply have mass points here. I mean, this picture is a little bit misleading because in the Gaussian approximation, you just have mass points. So there's no excluded volume. You have a spring constant in between, which says the bonds can wiggle a little bit around with a spring constant K here. You might have an equilibrium separation, but you can also put this to 0. And for this model, you can compute the partition function exactly. So the random walk and the bead spring model generate basically the same partition function. So we should see the Gaussian distribution coming out naturally, which I was showing you in the theory part in the beginning. Now, what happens if we are not in a theta solvent, but we are in a good solvent? Well, as I said, then we have to give interactions to my mass points, and normally you take the repulsive part of Lennard-Jones potential, so the Weeks-Chandler-Anderson potential, which is basically just here the purely repulsive part. So then you have excluded volume interaction, and what people in polymer theory often do is, or not only in theory, but also for the computations, you apply for the spring constant, you don't take an infinitely extensible spring, but you do one which has a finite extensibility, and this is called the Fine potential, and it stands for finite extensible nonlinear elastic bond, meaning that you have a nonlinear spring with a finite extensibility, and if you do that together with the Weeks-Chandler-Anderson potential, then you see the total potential confines your monomers to wiggle inside this non-harmonic potential, which has a cutoff basically at very low R's and a cutoff at very high R's. So this potential is sufficient to avoid bond crossing, and this is the standard potential for coarse-grained polymer simulations. It's called the Kramer-Grest model because Kramer and Grest were the first one to suggest that, and it's the standard model for doing polymer melts. The standard Kramer-Grest parameters are basically that you choose 1.5 for the sigma for the R0 and 30 epsilon over sigma for the spring constant. It's a very efficient method, and the sizes of these melts nowadays can be pushed up to a few hundred chains of 300 to 400 beads each. Longer you can't really go because the relaxation time of these polymers scale unfavorably with n to the 4, depending if you have hydrodynamics in or not. So this is a cutoff, and what you can study then in these melts is actually that the diffusive motion of the polymers follows this idea of reptation, namely that the other polymers form a cage in which the polymer can only move like a snake, and to see how the polymer motion in a big melt is. You can see these pictures here out of this original paper in the 1990s. And a more recent version is basically seen here in this movie, taken out of the Science article of 2004, where they have modeled a very large polymer melt. And now what they did there is a primitive path analysis in order to figure out the elasticity of polymer melts is thought to come from entanglements. That means you have a big bowl of spaghetti where your polymers are, they entangle sometimes just because they are self-avoiding chains. There is a tendency that they entangle, and this leads to elasticity. And you can see these entanglement, and people are interested in these entanglement lengths because then they are related to the rubber elasticity. And you can do a primitive path by saying, okay, I would like to take all the other chains away and see, pull a little bit on these chains and see where they have entanglements. And you basically see how these entanglements look like in this little movie. And from this, you can, for instance, extract entanglement lengths and so on. Let's look now at polymer chains in poor solvent. The poor solvent can be modeled via a full Lennard-Jones potential. You have a monomer attraction between the monomers because they like themselves much more than the solvent, so they would like to crumple up. And the quality of the solvent you can change via changing the strength of the epsilon parameter and varying also the cutoff. So that's for technical reasons. And via this, you can create polymer chains in a poor solvent, which then would obey this different scaling law as I've shown you before. Now, the last one which we would like to look at are the charged polymers. And there you do the obvious thing. You put charges on some of the monomers in your chain. You can also put them on all of them, and it would be a fully charged chain. But because you put charges on the monomers, there are also these counter charges called counter ions in the solution. We would be in an implicit solvent model, meaning that we would have also the epsilon of the solvent as a simulational parameter. Otherwise, you would just take the Krämer-Grest spring, and the idea is that you have modeled now, for instance, like a sulfonated polystyrene bead, which you see here, where the sodium can dissociate and being then the counter ion. Also here you can change the solvent quality by going from a Weeks-Chandler-Anderson potential to a full Lennard-Jones. So there are poor solvent polyelectrolytes also in water, even if they have charges. Namely, when you take now less and less charges which are sitting on the backbone, then the polymer as a total becomes less and less hydrophilic. So therefore, the water as a solvent becomes more and more poorer, to the case when these chains can also no longer sustain themselves to be dissolved in water. Now we are very close to the end. I just would like to tell you that there are also sometimes you have difficulties equilibrating polymer melts. I mean, this is a particular thing about polymer melts because you are so densely packed, and if the chains become very long, you can envision that the polymers have very little space where to move and to diffuse, and that in the simulation it will take forever. I mean, also polymers probably can rearrange on the level of seconds and minutes, depending of how dense these melts are. Because they are glasses, or if you're close to the glassy state, of course, it can take forever. Also, glass can move over centuries, but you, of course, don't have the time to wait or to simulate that on the computer. So if you would like to equilibrate these very slow, relaxing polymer melts, then it might be advantageous to add also Monte Carlo moves into your simulation. And there has been few suggested reptation moves or crossover moves where you actually change the identity of polymers. This, of course, you can only do when you're interested in only static properties. If you do dynamics, Monte Carlo is basically forbidden because you would change the dynamics. But as I said, this is only done to systems where the dynamics is so slow that you can't measure that in the computer anyhow. Now we are at the end, and let me summarize for you the main points. I mean, I gave you a few basic polymer physics concepts, how to theoretically describe polymers in solution or in the melt. There are polymeric diversities and the different statistics related to the good solvent, theta solvent, poor solvent case, and also to charged polymers. And I showed you a little bit on how to simulate them. So because this was rushing through, there are, of course, always textbooks, and polymers have been around, as I said, basically 100 years from now. And these are, let's say, Strobel and Rubinstein are really good books for polymer physics. And if you're a little broader interested in soft condensed matter, then this book by Richard Jones can be read. And with this, I'm at the end. I hope you enjoyed it. And if you have questions, please ask them in the question and answer session. Thank you.